Okay, folks. So today I'm going to talk about what we can learn about active galactic nuclei from the things that are in them. So uh, the work that I'm going to discuss today involves the contributions of a lot of people. Here's a picture from the before times, a partial group picture. We hope to return to that sort of state soon. There's also a long list of people, not fully complete, who are also involved in the work that I'm going to talk about over the last decade or so. Okay, AGN, what are we talking about? So here's a Hubble image of a quasar, and it looks for all the world like a nearby star has photobombed this Hubble image, right? So you see the kind of diffraction spikes sticking out, and it's getting in the way of whatever it is Hubble is trying to look at. But if you sort of look, there's a couple of clues that this is not the full story. You can see there's a sort of jetted structure out here. There's maybe some kind of fuzz behind the star-like thing. And if you take a spectrum of this object, you don't get a black body spectrum the way you'd expect from a foreground star, but instead you get a spectrum that's emitting across maybe 10 orders of magnitude in wavelength. You've got radio, infrared, a big blue optical bump, some X-rays. And if you look at the optical spectrum, you'll pick up some spectral lines that are redshifted by about 0.17 or so for this object. So this thing is sitting at about 3/4 of a gigaparsec from us. And so you can infer that basically this thing is shining with the light of 1 trillion suns. So it's outshining all of the starlight from its host galaxy. So let me move on. Here's another Hubble image. This is the ultra deep field. And you see loads and loads of galaxies. Some of them are blue, indicating a lot of star formation. Some of them are red, indicating that star formation is over and you've got a population of old stars. And we think that AGN, these bright objects that seem to generate jets and powerful outflows and all these other things, may impact the transition from things that look kind of like this to things that look kind of like this. So basically, because the AGN generates these powerful outflows, we think that has the ability to either physically push gas out from the inner bulge of the galaxy, or maybe heat it up so that it doesn't collapse to form stars. So we think that AGN play a role in quenching star formation in galaxies. And we think that basically the only thing that can really power these bright, super luminous objects is a supermassive black hole at the center of the galaxy, swallowing a whole bunch of gas and emitting a whole bunch of radiation and driving powerful outflows. So essentially the picture you want to have in your head is a supermassive black hole at the center of these things with a disk of gas on sort of parsec scales feeding the black hole. Okay, so in a nutshell, AGN turn out to be important galactic architects. If you're interested in the sort of small scale, the supermassive black hole right at the center, the AGN is a great way of growing the mass of the central supermassive black hole directly, just by piling gas on top of it. But you can also use it to bring supermassive black hole binaries together by exchanging angular momentum and causing supermassive black holes themselves to merge. In terms of the outflows that you'd expect from these systems, you'll get jets and winds and all kinds of things, and that will impact much larger scales in the galaxy. We see really interesting things like correlations between the mass of the supermassive black hole and the centers of galaxies and properties of galactic bulges. So things like the famous M-sigma relation, tell you that there's some connection between the supermassive black hole at the center of the galaxy and the properties of stars much further out. And we think that feedback is the connection between them. So, we've got these galactic architects kind of sitting at the center and impacting the galactic structure in which they sit. But these things are really poorly constrained. So even though we have electromagnetic observations across many wave bands, the basic properties of these systems are not particularly well constrained. So lifetime spans maybe 3 orders of magnitude you can play with. Gas density, more than 3 orders of magnitude. Size, the disk could be fairly small, it could be larger. Even the form of the disk, like the accretion structure that develops around the supermassive black hole, these are all pretty uncertain. So, just to illustrate the point, these are just some plots from a paper led by our students, Gaia Fabi, Saida Nassim, and Freddie Caban from last year. And, it just illustrates the problem, right? So, bottom panel, you've got density as a function of distance from the supermassive black hole for 2 fairly popular AGN disk models. Neither model is perfect, but it sort of illustrates the problem that, you're talking maybe 6 orders of magnitude in density within one AGN disk model, depending on where you are. The aspect ratio of disks, so the height of the disk versus the distance from the supermassive black hole, that's another parameter that people often use with these systems. You're kind of talking 2 to 3 orders of magnitude that you can play with just between these two models. So, this is a problem. These things are not terribly well constrained. So, the solution is that there are things in galactic nuclei. So the galactic nucleus isn't just a supermassive black hole with a gas disk or no gas disk. There are things there. And just to sort of illustrate the point, here's an image taken by the GES group of the orbits of some bright stars in our own galactic nucleus. And you can see this sort of dynamical mess of orbits, all orbiting something in here. Sag star, the supermassive black hole at the center of our own galactic nucleus. And you can kind of imagine that there are, these are bright stars, but there are faint things that are also in here, including stellar remnants like black holes, neutron stars, other things. And basically we think that the swarm of dynamically hot objects in galactic nuclei comes from the decay of globular clusters into the galactic nucleus, mergers, star formation, all kind of convolve together to give you a population that develops in galactic nuclei. Okay. So you can imagine that if a gas disk arrives in the galactic nucleus and you sort of fit it on top of this, you'd imagine that some of these orbits are going to be coincident with the gas disk, and some of them are going to be inclined and sort of punch through the gas disk. And so you'd expect to end up with a population of objects embedded in an AGN gas disk, just because there are things in galactic nuclei. So again, there are objects in inclined orbits punching through the disk. Over time, some of those orbits are going to be captured. So you won't just have a population that are initially coincident. You'll also add to that population as orbits get ground down. And again, this is a little panel from Fabi et al. From last year, led by our students, just showing you that basically modest inclination angle orbiting black holes can get pretty efficiently captured by AGN disks over a sort of reasonable amount of time. Okay, so if you end up with satellites in gas disks, we kind of know what to do with that. So protoplanetary folks have been studying this problem for a lot longer than AGN people have. And there's a whole sort of formalism that you can steal and apply to AGN. So basically, in protoplanetary disks, right, we know that you can get objects embedded in a disk. The gas sort of back reacts on the satellite and can torque the position of the embedded object. So essentially, instead of a closed orbit at a particular semi-major axis, instead your orbit turns into a spiral, typically inwards, but sometimes it can be outwards in the disk. And we call this migration. And you can imagine that if you have, say, a couple of objects that are migrating in the disk that get close to each other, their relative velocity at encounter can be small enough that you'll form a binary pretty efficiently. And a binary that would not otherwise form in the dynamically hot kind of mess of a galactic nucleus. So this is a really kind of efficient way of bringing things together that otherwise wouldn't live together and form binaries. So once you form a binary in a gas disk, there's sort of two ways that you can influence the size of the binary. One is gas. So the flow of gas around the binary can sort of make the binary shrink, or can make it expand. I'll get back to that. Or there can be encounters with other embedded objects in the disk. Things that pass nearby can encounter the binary and either harden it, make it shrink, or make it expand. So the important point about this, right, this whole process of migration and forming binaries, is that it depends on the properties of the disk that these objects are embedded in. So if there's an efficient way of forming binaries in an AGN disk, that's telling you something about the properties of the AGN disk itself. So, here's the surface density. Over here is the aspect ratio, your position in the disk, the mass of the object, the mass of the central thing, right? So basically, you can use the properties of binaries that form to tell you something about the gas disk in which you form those binaries. Okay. So, yeah. So about, I guess, 7 years ago, so we predicted that embedded black holes in AGN disks could find each other, form binaries, and merge, and that population of merged black holes could be detected by LIGO in gravitational waves. You get this population of overmassive black holes. And there's sort of been an explosion of interest in this sort of channel since then. A lot of groups, including ours, doing work. I'll point out Imre Bartos's group down in Florida is doing very good work on this across a range of topics. Hiromichi Tagawa has done an excellent job on Monte Carlo simulations of these systems in AGN. In our own group, Amy Secunda has spent a lot of time thinking about n-body simulations of these objects and how their mergers are going to go. I've tended to focus on Monte Carlo simulations of mergers that might happen. And there are some groups in Europe that are working on dynamics and rate calculations. I would say sort of broadly, for several decades, we've known that things should live in AGN disks. That idea goes back to the 80s and 90s. And we've even known that they should migrate. But I'd say kind of the takeaway from the last decade or so, all of this body of work, is the things in AGN disks are going to merge with each other. Those mergers are detectable in gravitational waves and maybe even electromagnetically. And third, the population of mergers that you get from this allow you to reverse engineer both the disk properties and the properties of the nuclear star cluster that lives in the galactic nucleus. So we get some lever arms on things that we otherwise wouldn't be able to measure. So, Okay, so say you make a black hole binary in an AGN. What happens then? So I've stolen this little cartoon from Carl Rodriguez because it's really neat, and it kind of illustrates some key points. So you get a black hole mass m1, and it's got a spin magnitude s1 and an orientation pointing whatever way it's pointing. Black hole mass m2, different spin, different magnitude. Great. The binary orbits around its center of mass, giving you a binary orbital angular momentum L. And if you mass weight the spins and then project them onto L, you get this little green arrow here, chi effective. And that's something that LIGO can measure reasonably well. And so this is something that we'll come back to. In terms of sort of physical intuition for what's going to happen to your binary, you want to think about a couple of things. There's gas around this binary, so these two objects, mass m1 and mass m2, are going to accrete gas. That's going to torque the spins towards alignment with the orbital angular momentum of the gas of the disk. So this arrow S1 is going to torque. This arrow S2 is also going to torque. That's going to depend on how much gas you can kind of cram onto these things. The other thing that's going to happen is that the orbital angular momentum of the binary is also going to be torqued into alignment with into alignment with the orbital angular momentum of the AGN gas disk. And those processes, that process of torquing the orbital angular momentum into alignment with the AGN, that again depends on the disk properties. So this thing here, H, that's your aspect ratio, just how thick your disk is compared to how far out you are, surface density, and your position in the disk. So that process where you're kind of torquing the orbital angular momentum of the binary depends on the gas disk. Great. But there are other things going on as well, right? There's that sort of spherical component of objects that are plunging through the disk. If one of those orbits comes close to our binary here, that can torque L away from alignment with the AGN disk, right? And then there's a second component of orbiters, the other objects that are also embedded in the disk and migrating. And they can weakly or strongly dynamically interact and also torque L. So there's kind of this competition between a gas damping process that tries to get things into alignment and then this dynamical process that's fairly random and isotropic that's trying to kind of kick you away randomly and will send you on a random walk. And that latter process basically depends on the properties of your nuclear star cluster, the properties of the things embedded in the disk, and then the properties of your binary, right? How big your binary is, how massive it is. So there's a competition of torques, and that competition is probing both the disk and the overall population of the nucleus. Okay. Oops. There we go. So I mentioned that there's two things that can change the size of the binary, that can shrink it or expand it. So one thing that can do that is gas. So here are just some figures that I took from a relatively recent paper, sort of illustrating some of the points. So this is a 2D hydro simulation of a pair of black holes in an AGN disk. And the upshot of this simulation is that when you look inside the Hill sphere, the sort of zone of influence of the binary, and you track the gas flows, whether this binary shrinks or widens depends on how well you resolve the gas flow right in here and right in here. It also depends on the way the binary is rotating, whether it's rotating prograde or retrograde compared to the gas flow, and the softening length involved in the simulation. So what I will say is this is 2D. Things will change if you add a third dimension, right? The gas is going to flow differently. Um, and this also doesn't involve feedback. So it's assuming that gas just flows onto point particles in here, and there's no heating up of the gas as it flows in, and there's no distortion of the gas flow from feedback from these things. That's going to change this picture a lot. So our very own Jan Fay and Phil, together with Leah Hankla, have thought about this problem. So if you stick a satellite in a gas disk, then feedback on the surrounding gas results in a blob of gas around the embedded object. Because the disk is shearing, because the inner disk is rotating faster than the outer disk, and because there's a pressure gradient in the disk, you'll basically end up with an asymmetric blob of gas around the embedded object. What that does is it provides a torque on the embedded object, and that torque can be comparable to that migration torque that I told you about that sort of can move things inwards typically in disks. The difference in this case is this torque prescription mostly acts outwards. And so now we have this extra complication that things that might otherwise smoothly migrate inwards can, depending on the disk properties, maybe migrate outwards. So what I've done is I've applied Jan Fay and Phil's prescription to one of the AGN disk models that I showed you earlier. Here's the ratio of the heating torque from feedback to the migration torque. So again, the heating torque tends to be outwards. The migration torque tends to be inwards. If the value of this ratio is bigger than 1, things will move out. If the value is less than 1, then things will move in the disk, but slower than they otherwise would. So what I did was I applied this setup. I took the prescription and I applied it to some of our Monte Carlo simulations just to see sort of what would happen. And, the right-hand panel essentially shows you that it doesn't make that much difference. What basically happens is instead of getting a smooth set of differentially migrating objects that encounter each other, form binaries, and kind of build up a hierarchical set of mergers that way, instead, you get much more of a sort of Brownian motion effect where some things are going to be migrating outwards, other things are going to be migrating inwards, and you get a more randomized sorting process. The net effect of which is that you get maybe a little less massive black hole binaries forming in this setup, but maybe a little bit of a pileup at sort of intermediate masses. But this is sort of work in preparation. If you invite me back in the fall so I can do this in person, I'll be happy to tell you the full results of what we find in our analysis. So gas is not the only thing that can, harden a binary, bring it closer to merger, or soften it. In AGN disks, there are multiple objects, all migrating and all potentially encountering each other. And dynamical encounters can be super interesting. So I stole this cartoon from a recent paper by Johan Samsing. So you see the supermassive black hole in the center, lots of things orbiting around, and you get a three-body encounter somewhere in the disk, and it leads to this kind of complex, messy encounter, and eventually some sort of eccentric merger as a result, and a scattering. So dynamics can be super complicated. How complicated, you ask? They can be chaotic, literally chaotic. So, Johan has come out with these amazing phase space diagrams for the results of numerical experiments of planar scatterings. So basically you set up a binary, it's got a particular separation, you send a tertiary in to encounter it in 2D. You set up zero eccentricity initially. Sometimes you fire the tertiary on a prograde sense, sometimes in a retrograde sense. You set up the binary at different phases, and you end up with this chaotic kind of mess of possibilities depending on the exact arrangement of the system. So in a lot of cases, things remain the same. So a binary can harden, and the scatterer can fly off with a bit more energy. Binary might soften, and the tertiary loses some energy. Sometimes you'll get rapid two-body mergers. Sometimes you'll end up with weird three-body sort of setups where you'll get two mergers in a row. Sometimes you'll just swap out something in the binary for the tertiary object. But essentially you can get kind of a really chaotic, strong encounter with a wide range of possibilities, including things like eccentricity. So on the right-hand panel, there's a distribution of eccentricities that happen in mergers, and it basically shows you that by the time you get into the LIGO band for these sort of 2D encounters, there's a reasonable fraction of events, maybe a third of events, should have some sort of noticeable eccentricity. Now, this I'd say is an upper limit. AGN disk orbits will not be identically in plane and uniform. So if you give it some inclination and you allow for the effects of gas damping, you're gonna shift this distribution to the left. But you should expect a greater distribution of eccentricities than in, for example, clusters and globular clusters. So, okay. So what I'm going to do is I'll just sort of walk you through a set of qualitative expectations from a variety of sources, simulations, some analytic work, and some other places, just to sort of, we'll kind of list our expectations before looking at what the data tells and what we can sort of reverse engineer. So let's start with how masses evolve. So this is a pretty simple arrangement. It's from a paper we put out last year on Monte Carlo simulations of mergers in AGN disks. You start with an initial mass function for your black holes, a couple of delta functions for your neutron stars, white dwarfs. You allow these things to migrate differentially in our model AGN disk. Binaries form and merge, and so you'll build up a population of more massive objects as that happens. So the initial distribution is in black. In red is the distribution after a mega year of this process going on. And there's a couple of things that you can see. There are more massive black holes being produced out here in a region known as the upper mass gap, where we think that stellar evolution cannot produce black holes. So you're producing this sort of merge population of more massive black holes right up here, including an intermediate mass black hole up here at about 200 solar masses. You're also merging neutron stars together in the disk and creating things below the lower end of our black hole initial mass function, sometimes called the lower mass gap. So essentially our expectations are, okay, after time, as the AGN disk sort of does its thing, you'd expect your initial mass function to evolve into maybe a broken power law with maybe some stuff at intermediate masses between neutron stars and black holes. Okay, what else? So let's put that up on the big board. That's our sort of expectation for masses. Cool. Intermediate mass black holes were something that sort of popped out of what we saw. You can definitely find areas of an AGN disk where the surface density is going to change quite dramatically, particularly in the inner regions because of radiation pressure. And when that happens, that migration torque that I was telling you about that tends to bring things inwards in the disk flips sign and tends to migrate things outwards. And so there are going to be some orbits that will trap objects. And so things will tend to end up at these locations in AGN disks if you give it enough time. And what that does is that allows for fairly large masses to build up at these locations in disks. So Gillian Bolivari was the first person to sort of point this out for some AGN disk models. And Amy Secunda has done a bunch of n-body simulations that basically show that the longer you let your AGN disk kind of merge things at traps, the bigger the mass that you can build up there, and the more extreme the mass ratio of mergers becomes. So, if LIGO sees bigger and bigger intermediate mass black holes, you're kind of probing this bit of AGN disk space. You want your disk to live a bit longer, so you end up with more stuff in that trap. If LIGO doesn't see things in this region, then that also tells you something for the AGN channel, right? It tells you that AGN disks can't live that long, or so long that you build up enough mass in one place. Okay, cool. So let's put that up on the big board. What else we got? What else are we expecting qualitatively? So again, from the paper from last year, the number of mergers that you would expect in AGN is going to grow, right, as time continues. It grows at one rate away from the trap, and it grows at a different rate in the trap. So the ratio of trap to bulk disk mergers is going to depend on the lifetime of your AGN disk. But if you sort of say the AGN disk episode lasts about a mega-year, you'd expect about 10 times the number of mergers in the rest of the disk away from that trap I was talking about to the mergers at the trap. And remember, these are the ones that can kind of build up your intermediate mass black hole. These things are just common or garden first generation black hole mergers. You take two random black holes, shove them together. There's your merger. Well done. Okay. So, most mergers are going to be in the bulk disk, not at the trap. So this is going to be the base of your hierarchical model pyramid of mergers. So most of your mergers are going to be low mass coming together. The tip of your pyramid is going to be your intermediate mass black hole formation events. Okay, cool. So remember I mentioned this chi-effective parameter, that projected mass-weighted spin onto the orbital angular momentum of the binary. This is something that LIGO can measure pretty well for binaries. The expected distribution of that is for the AGN channel. It's two components. One for mergers in the bulk disk is this sort of narrow peaked distribution centered around a chi-effective of 0. So what that means is that the little green arrow is small, so your black hole spins are typically misaligned. They're not terribly well aligned. They're not like this. So they're typically misaligned when you bring them together to make that small projected chi-effective. Some of them are negative, which means that the net projection, okay, I can't twist my thumbs quite that far, but if you have the black hole spins oriented a different way, you'll get a net chi-effective pointing the other way from the orbital angular momentum. So in the bulk disk, you get a narrow chi-effective distribution. For mergers at the trap, because you're making multiple massive objects, you'll create rapidly spinning black holes at the trap. And sometimes if the binary that forms this object is prograde, the rapid spin will end up projecting along L. If it's retrograde, it will point the other way, as sort of anti-L. And so you end up with this broader distribution that you'd expect for mergers at the trap. But again, those trap mergers are going to be 10% of your total. So that's kind of the expectations for how that sort of projected spin thing should look from this population. Okay, so that's up on the big board. Yeah, so we have black holes merging not in the vacuum. And there's gas around them, which means there's the potential for possible electromagnetic counterparts. So there's a couple of steps that you need to go through in order to generate a detectable EM counterpart for these things. So first thing we need is gas. Check. Got that free. If you want to see the signal, then you're going to need either a really thin disk so that you can kind of see down and see what's going on, or you'll need something like a kick that will take you out of the optically thick disk midplane and into a sort of thinner atmosphere. Okay, let's say you get a kick from your black hole merger. You send this merge product into the disk atmosphere. We can now see it. Is that good? No, it isn't. You still need your signal to be luminous compared to this bright AGN disk that you've emerged out of. So you need a naturally luminous signal from whatever's producing it. And you then also need to distinguish the signal you've just generated from false positives. So the AGN varies, right? There's going to be some panic at the ISCO and variation at small radii in the disk. There are supernovae. There are microlensing events. There are TDEs. So you need to be able to distinguish the signal that you predict from false positives. Over here on the right-hand side is a plot from a paper from 2 years ago, where basically, it essentially says that further out in the disk, you could potentially detect above a sort of fiducial detectability threshold. You could detect maybe some shock gas from these mergers, but your odds are better for detection in lower luminosity AGN. So these dashed lines indicate lower luminosity AGN, solid lines, higher luminosity AGN. So basically, it's easier to detect bright things against faint things rather than bright things against bright things. But you already knew that. For black hole neutron star mergers, we're going to need the same sorts of things as for black hole mergers. So you'll need something like a very thin disk. That's possible in some AGN disk models, or a kick out of the midplane. Otherwise, if you don't get kicked out of the midplane, all of that luminosity that you generate from your signal is just going to get washed out into the infrared and emerge over a time scale of years. So, it's going to be really hard to pick up these things if you can't get out of that dense, optically thick midplane. Also for black hole neutron stars, we'll want something like a reasonable mass ratio. So you shred the neutron star before it gets swallowed so that you get some sort of electromagnetic counterpart. And Rosalba has done some work on exactly this problem for AGN disks. Okay, so cool. We've added that to our list of sort of qualitative expectations. Stay with me. We've only got 2 more. We're not just going to get black hole mergers in AGN. You're taking all of the ingredients of your nuclear star cluster and you're kind of running these things together randomly. The ratio of black hole mergers to black hole neutron star mergers to neutron star mergers is something that depends on the gas disk properties, but it also depends on the cluster properties, right? The ratio of these objects, black holes to neutron stars, to regular stars, is going to depend on whether your mass function is steep or shallow, whether your nuclear star cluster is cuspy, the density increases as you go towards the supermassive black hole, or whether it's been cored, whether you've lost a bunch of stuff from maybe a supermassive black hole merger that's cleared out a bunch of small mass objects. So the ratio of, black hole neutron star mergers to black hole mergers can depend on whether you have a mass function that goes to low mass sort of continuously, so you get a lot more low mass objects. But if you get a bunch of mass segregation in your galactic nucleus and you deplete the low mass objects, then you're going to get more black hole mergers in your AGN than black hole neutron stars. One thing we find from our simulations is that the neutron star mergers that LIGO is detecting cannot come mostly from AGN. Definitely AGN are not the dominant contributor for that. Black hole binaries and black hole neutron star binaries might still be the dominant contributors, but neutron stars cannot be. Okay, that was the sixth thing. There's only one more, and that's that stars in AGN disks are weird. So this is from work by Alex Dittman and our very own Matteo and Adam. So the idea here is that if you take a star and you stick it in an AGN disk, it will evolve very differently from in vacuum. You change the boundary conditions on the star accretes gas, and essentially you can grow the mass of the star, but there's enough hydrogen in it that it won't die. And so you can end up growing large, several hundred solar mass stars, depending on where you are in the AGN disk, which will affect the disk itself. So you can start off with regular main sequence stars and grow these monsters that are going to live in your AGN disk. These things are also going to experience migration torques. They're going to heat up the disk. They're going to disrupt the migration of other things. They will merge with other objects, including themselves, but also with black holes. So AGN stars are a new sort of piece of the AGN puzzle, but they're another angle at getting at the properties of the AGN disk, and a very important one. So what we've done is we've basically summarized, here are expectations, right? We expect a mass distribution. We expect some intermediate mass black holes. We expect that most mergers are going to be first generation random things sort of slammed together. A small fraction will be the tip of the merger hierarchy, leading to more massive events. The projected spin, that little green arrow that I was showing you, should be symmetric about 0. There are potentially M counterparts. The ratio of different kinds of mergers can tell you something about the AGN disk, but also the nuclear star cluster it's in. And these massive blue straggler stars impact the AGN disk and the post-AGN. Okay, so before we get to the data and what the data say, how do we separate AGN from other channels? So there are other ways that you can generate black hole binary mergers. One way, field binaries. Broadly, I'm not going to get into it, but broadly you would expect that chi-effective parameter to be greater than 0. Essentially, spins can't be too badly misaligned from two stars that evolve in the field and then merge within a Hubble time. But, supernova kicks are a problem. I'm not going to say anything more about that. Cluster dynamics, essentially that's running objects together in clusters. You'd expect an isotropic distribution of spins. But if you see something like an intermediate mass black hole, you would imagine that you'd need a fairly deep potential well to hang on to the previous merger products that go into making the intermediate mass black hole, unless black holes are born with nearly zero spin at formation. All right, that's the other ways of making black holes. AGN, you want to think about as starting off like clusters, so random things being jammed together at random orientations. But there's a symmetry breaking, there's a torquing towards alignment over time. And the magnitude of that torque depends on the density of the gas disk. The longer the AGN lasts, the sort of greater that alignment is going to be. But you're also probing the properties of the nuclear star cluster that can torque things out of alignment. So there's a sort of complicated competition that the AGN channel is probing. Okay, let's get to the data. What did LIGO find? A whole bunch of black hole mergers. So in blue are the LIGO Virgo black holes. I'm going to focus on two of the weird things, the most massive merger that LIGO saw, and sort of the widest mass ratio event in LIGO's results. Okay. So first off, GW 1905-21, it's the first detection of an intermediate mass black hole formation event. And this cartoon suggests that, so this event consists of an 85 solar mass and a 66 solar mass black hole merging to form something about 150 solar masses. This is an intermediate mass black hole. These masses, the 85 and the 66, are in that upper mass gap where we think that stellar evolution can't produce black holes of this mass. So you might think that these objects are the result of a previous merger of black holes. If that's the case, then you can imagine that if you merge two black holes to produce the 85, and you merge two other black holes to produce the 66, these objects, when they form, should have a kick at merger. And so in order to hold on to these two things, in order to merge them again to make your 150 solar mass object, you'd need a deep potential well. So, something like a galactic nucleus is reasonable, and AGN is pretty plausible. There's some evidence for high spin for these objects, again suggesting that maybe these are hierarchical mergers. So this could easily be an AGN event. There was an EM counterpart detected by candidate counterpart, I should say, observed by ZTF. We found a weird flare in a particular AGN in the LIGO search, in the LIGO error volume. It's weird enough that it's on the order of 1 in a million for AGN that have been looked at by ZTF. That could mean that we got unlucky and that we saw a 1 in a million flare, right? But it's also possible that it could be a EM counterpart to this extreme merger event. If you want to explain the luminosity of this flare, because the host AGN is pretty bright, you need something like a jet associated with this merger, a sort of very high mass accretion rate and a jet, in order to explain the luminosity of what we see. Fermi did not see any high energy photons associated with this event. The fact that it didn't doesn't mean there wasn't a jet, but it means that this event is a sort of big fat maybe. If you want a potential false positive to explain this, I would say your best odds are a combination of false positives. So a combination of a microlensing event plus a flare in the source at the same time. They give you about 1 in 10 million chance. We could have just gotten unlucky with this. There are more candidate counterparts. I am not at liberty to share the details of any of these, but if you invite me back in the fall so I can do this in person, I will be happy to share more about the other candidate counterparts that will hopefully be coming out within the next couple of months. Okay. So the other LIGO event I just wanted to briefly focus on, GW 190814. It was a black hole merger where is either a black hole or a neutron star or something kind of in that lower mass gap. There's a high implied merger rate associated with this type of merger. From the perspective of the AGN channel, a mass ratio of 10 to 1 is expectation for black hole neutron star mergers. So if this is a black hole neutron star merger, like this is what you'd expect from an AGN. If it's a black hole merger, a 10 to 1 mass ratio is about sort of 5% occurrence in the bulk disk. So if you kind of put those two weird LIGO, those outstanding LIGO events together, 1905-21, if it was a trap merger, a merger at an AGN migration trap, it would imply that about a quarter of all black holes that LIGO is seeing are coming from an AGN mass merger hierarchy. If you think that 1908-14 happened in an AGN, if it's black hole merger, it implies most of what LIGO is seeing is coming from AGN. If it's a black hole neutron star merger, it implies a sort of plain vanilla galactic nucleus with a little bit of mass segregation. Black hole merger rate sort of somewhere in a modest fraction of the total rate. Okay. For the overall population of mergers that LIGO sees, this cartoon shows a bunch of mass models that they tried out on the entire population mergers they saw. If you remember, we're expecting a sort of broken power law distribution, maybe some stuff in the lower mass gap. Basically, that's allowed. As far as spins, the chi-effective distribution is narrow-ish, but it's biased towards the positive. So it's not centered around 0. However, the fact that there's a sort of preference for a negative component is suggestive of dynamics. So it could be that between 25% and maybe 90%, if you kind of fold the negative part of this distribution into positive, it could be that up to 90% of the mergers that we're seeing could be explained by, say, a dynamical merger channel, which could be globular clusters, but could also be AGN. Okay. So, okay, let's say we get a phone call from the aliens who run this simulation that we call our universe, and they say that, okay, you know what? Well done, guys. It's AGN. That's it. So what could we reverse engineer? What can we say about the properties of these things? So if we make an extremal assumption, just say everything is coming from AGN. It isn't, because that's not the way the universe works. But let's just assume it. It tells you that AGN can't live super long. Otherwise, all of those spins would tend to get aligned, and you get a large positive chi-effective distribution. And so, the AGN lifetime has to be, on average, in these systems, less than 5 megayears. But you also need the AGN disk to live long enough that you merge these things efficiently, so probably greater than half a megayear. So you're kind of saying half a megayear to 5 megayears in duration. AGN gas disks have to be dense enough to sort of capture enough objects from the nuclear star cluster to make these things, to make binaries, migrate them, and merge them. So we're talking a density of, greater than 10 to the minus 11 grams per cc, kind of modest thickness. Another thing that sort of stands out from the data is, again, if you assume they're all from AGN, disk dynamical hardening has to be important, right? That asymmetry in the chi-effective distribution tells you that you must be preferentially biased in favor of hardening prograde binaries versus retrograde binaries. And that's something that I'm trying to build into Monte Carlo simulations right now. So again, if you have me back in the fall, I can tell you more about those results. The nuclear star cluster interactions, that spherical component kind of plunging through the AGN disk, that's also important. So these mergers are happening in fairly dense nuclear star clusters. If you look at the rate of events, they have to be happening in the brightest AGN, quasars and Seyferts. So that's kind of a yay for identifying fewer objects in a LIGO search volume, but because it's going to be harder to detect EM counterparts directly if the AGN is intrinsically bright. So you can also turn the knobs the other way for all of this and basically say, if none of them are from AGN, you can kind of come up with an alternative parameter space for AGN, lifetime density, and so on. I think I'm just at my time. Or actually, no, I'm over. Thank you, Callie. So, in conclusion, the big take home is mergers of things. There are things in AGN disks. They can merge. Those mergers are detectable in gravitational waves, potentially in EM. And the properties of those mergers tell you something about the properties of the disk and the properties of the cluster that allows these mergers to happen. And I will leave it there. Thank you all so much.
Thanks, Barry. Sorry, I was engaged. Go ahead, Masha.
Hi, Barry. Thanks for the talk. So when you were sort of setting things up in terms of the compact objects that were in the AGN for neutron stars, you used a delta function for their masses. And I was wondering, because the neutron stars we've detected, have some width to that distribution. And I wonder how sort of sensitive this picture is to that.
Yeah, that's a great question. So the simulations that I showed you are sort of, zeroth order 1D simulations. They're sort of a starting point. We picked 1.3 solar masses for the neutron stars because that's, those are neutron stars that we observe. The width, so the effective width of the delta function, it's not infinitesimally narrow. The mass spinning that we use in our simulations is 0.5 solar masses. So effectively it's, 1.05 to 1.8, essentially centered on 1.3. But yeah, one thing that, again, if I get time, I'd like to play with what the neutron star mass distribution is and feed that into the population of mergers that we expect. And so that'll kind of blur out the ratio of masses of black hole neutron star mergers. That's what I'd expect anyway.
Thank you.
Rachel?
Thanks, Barry, for this fascinating talk.
Cool.
I was wondering what you really mean by the lifetime of the AGN, because it's shining or not shining, the black holes don't care about that, right? They only care about whether the gas disk is there and whether it's dense. So are you telling me that I have to destroy my whole accretion disk every 0.5 to 5 megayears? And is that consistent with what we know about duty cycles of AGN and the Sultan argument and all, yada, yada, yada?
Yeah, absolutely.
This is kind of like rocking my world.
Yeah. So that's a great question. Yeah. So sort of in astro kindergarten, we were told that AGN would live for 100 megayears, and and you get one go, and it just all happens, and you're done. What we're seeing from observations particularly optical and X-ray observations, are that there are dramatic changes in AGN that occur on short timescales. And those are suggestive of systems that are bright but short-lived. And so our picture is kind of evolving from that, astro kindergarten version that we had of a single pulse from maybe a torus that feeds 10 to the 6 solar masses onto a supermassive black hole that lasts 100 megayears. Rather, there are instabilities in your fuel reservoir that can fuel pulses of low angular momentum gas. In some cases, those pulses of gas may be small, right? 1,000 solar masses, you accrete it quickly, and you have this short-lived AGN episode. You still have a reservoir there that can feed more pulses of gas inwards. It could be that you get multiple pulses so that the instabilities in the fuel reservoir sort of generate a long-lived episode, a long-lived AGN episode. As all of these kind of pulses all blend together that give you a disk. There's also, I didn't get into the state of the accretion disk. The mode of accretion. You could have an accretion mode where you have a fairly radiatively inefficient accretion disk. Those are expected to be puffier. If you're going to merge things efficiently in disks, you need a pretty dense disk in order to make this stuff happen, to migrate these things so that they encounter each other, so that you make binaries at a reasonable enough rate that they can, either gas or dynamics kind of knocks them over the threshold and LIGO detects them. I think it's fair to say that from EM studies, our picture of AGN disk lifetimes has changed, and that the sort of the picture I have in my head now is of a sort of power law of mass accretion episodes. Maybe a lot of them are low mass. There are some long-lived pulses that generate long-lived AGN, and sort of everything in between. And so essentially, if you want to maximize this merger rate from this channel, you do best by having multiple episodes where you get multiple bites at the cherry to merge these things together and generate a high merger rate. Essentially, if you have very long-lived AGN, like the way we were taught in astro kindergarten, right? You'll align all of the spins, all the black holes will be captured, they'll all be merged, and then they're gone. And then there's no more mergers, and the AGN is still there, right? So you want these, in order to really bump up the rate and explain what we're seeing by this mechanism, you need these sort of shortish-lived dense disks.
Thanks, Barry. Lots to think about.
Yeah. Ruth, you made a comment in the chat. I'm not sure if you wanted to pipe up.
Yeah, sure. We do have specific lifetimes for some categories of AGN, such as FR2s.
Yeah.
And there are definite lower limits on the lifetimes of about 10 to the 7 to 10 to the 8 years.
Yep.
And similarly for the FR1s in clusters of galaxies.
Yeah, one of the interesting things is sort of trying to deal with the evidence that's sort of building from the optical side of these short-lived AGN episodes where, the O3 lines that come from, material that's responding to the AGN sort of much further out are not there, right? And they tell you that basically your AGN has only been on for 10 to the 4 years or something like that. It hasn't been going for very long. versus systems where we can see these huge jets sort of sticking out. Maybe those jets are a series of events that all sort of add together and create something that's super long lived. Or maybe, but yeah, I mean, definitely there's a wide range of lifetimes, but disks like that are tens of mega years, maybe 100 mega years in duration, you'll get your chance to merge things in the disk, and then kind of you're done. You're not going to generate a high rate of mergers, or at least not the merger rates that the LIGO sees.
Well, I think just from the perspective of what do we know about the lifetime of AGN disks, I mean, my interpretation, and I thought the general interpretation of people in the field for changing look AGN, they're not concluding that they're turning off. They're continuing to be AGN, but they're changing state. And actually, I heard a really interesting talk about that yesterday. It's very rare. It's not something that happens in many AGN. And the current thinking is that it's related to magnetic field structure.
Yeah, there's a whole rabbit hole we could go down with this. I think from the optical side, I know, for example, that ZTF is detecting AGN with no narrow O3 lines, which tells you that basically the AGN has only been active for 10 to the 4 years or so. So, there's clearly this wide range of activity in these, around supermassive black holes. It's not all long-lived. It's not all short-lived. And it's, it's a big AGN universe out there for sure.
Absolutely.
Let's take another conversation from another question from Will.
Yeah.
So Barry, I wanted to ask, when you were talking about electromagnetic counterparts, and in particular with reference to 1905-21, it really kind of seemed like you were threading a needle a little bit. Like you need a dense disk because you got to dissipate a lot of energy in the disk, but then you can't have a dense disk because you need to have, either optically thin or things happening near the surface. And so, I'm just curious, like I know in the paper with Graham, you have careful estimates of the, false alarm rate of this thing, and does it really look reasonable, and how often should this happen, and so on. But like now go to Vegas and you're at the casino window and like, is it real? And should we expect to see a lot of counterparts like that? Or did we just get phenomenally lucky if your answer is, yeah, it's real?
So those are great questions. Yeah. I sort of go back and forth on this one. My experience with AGN observations leads me to be pessimistic because AGN do stuff. We could just have got unlucky at the 1 in 10 million level. It's weird though. And so, I don't think we have a good self-consistent picture of how you can generate something of that luminosity in a black hole merger. I think a lot of work needs to be done on particularly high accretion rate black holes, right? You need, in order to make this thing work, you need your merger to have happened in the dense disk midplane. You need that object that was formed to be kicked out of that midplane so that you can see what's going on. But you need to drag material with you and accrete it onto that kicked object. And then you need light to get out from that kicked object, right? So you need something like a jet to penetrate the murk and get that radiation out. So, you know, that's a lot of knobs to turn, right? So, you know, on on optimistic days I go maybe. On pessimistic days I go, probably not, you know. So I think, you know, the other candidate counterparts that are going to come out in a couple of months, I think will help us sort of understand a bit more what weird types of events we can pick out and maybe tell us something about mergers, but also maybe just tell us something about weird AGN variability, right?
Okay. Yeah. Thanks, Barry.
Sure. Yeah.
Ryan?
Thank you for the talk, Barry. I just want to say thank you for publishing this counterpart. I think, you know, it's definitely generated an enormous amount of thought as to how to do this, and I think it's the right thing to do, and we'll remain skeptical for various reasons, but
Yep.
I think it's been a very positive thing. And I guess my question is partially to you and partially to Will. I was thinking about this more during your talk. How confident are we that 190521 was really a binary black hole? There are other scenarios proposed by Masaru Shibata that it could be a very massive star that formed a very massive accretion disk around it. And so I guess my dual question is, have you thought about these types of very massive, rapidly rotating stars and whether they would exist in these disks? I think we can talk more about this on Monday. And then also for Will, whether he buys this Shibata scenario, because this very massive black holes are basically just like bursts in LIGO. So I guess it's a question of how certain we are of that, because it may actually be easier to get a bright counterpart out of Shibata's scenario than from a black hole merger for the reasons you mentioned.
Right. I can go first and then Will can follow up. So I was just in fact talking with Matteo earlier about these supermassive stars in AGN disks, and we can chat a bit more on Monday about this. But one thing that I find really intriguing is that if you have these immortal blue stragglers forming in AGN disks, then those things will migrate in the disks and they will encounter black holes. And so you should expect black holes to end up inside these objects. So creating these, you know, Thorne-Zitkov, you know, analogs, right? Except you've got a little black hole at the center of your undying blue straggler. And sort of there's an EM signature that you might expect to happen if you had two black holes merging inside one of these supermassive stars. If you merge a black hole and you send it flying off as a bullet with a kick, then conservation of momentum means that the star has to sort of jerk sideways into the AGN, and so maybe you generate some interesting EM counterpart from that. But that's a whole other discussion that we can have on Monday. But I'll let Will say stuff.
Yeah, I think, you know, in answer to the second part of your question, Brian, about 1905-21 specifically, like, you are absolutely right that it's a wiggle or two and then a damped sinusoid. And it's very hard to gesture at that convincingly and say for certain that it comes from a black hole merger, as opposed to some other source that has the right kind of frequency of emission. That said, you know, I think we've seen an awful lot of binary black hole mergers. It's really easy to tell a story about these things are quite common and fine. You know, the masses are high, so they live above the pair instability threshold for, you know, stellar origin black holes or whatever. But it just strikes me kind of like in an Occam's razor sense, we don't need to invoke something weird to make 1905-21. You know, that's not to discourage people. In fact, I very much liked what you said to Barry about thank you for publishing the counterpart. You know, even if you doubt it, maybe on physical grounds or something, like, you know, it's worth thinking about weird stuff. You know, I'm not trying to discourage people from writing papers about 1905-21 as a weird source. It's not two black holes. But I think the story's so easy to tell that my bet would be on the binary black hole merger scenario. You know, in the end, you collect a bunch of these and you stack them on top of each other and you try to look for minute features that might suggest differences between various scenarios, and you hope that you can distinguish them. But, you know, we're not at that state yet.
Thank you.